Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is Lecture 2, Part 2, and we're going to call this video 04B. And in the last video, we discussed how to do an approximation of the binomial distribution using the Poisson distribution, and this was different because we were now using a discrete distribution to approximate another discrete distribution and didn't have to use the continuity correction. We also went over the definition of convergence and Schiff's theorem. In this video, we're going to do some examples of approximating the binomial distribution using the Poisson distribution, and we will look at an example of how different sample sizes affect the moment generating functions. So let's get started. All right, let's do example number 1. So we're going to let lambda equal 5, okay? And this is for a Poisson distribution and say, or Poisson random variable x. So x is Poisson lambda equals 5. So now we're going to let NP equal 5. Remember, we need to set NP equal to lambda. And we're going to do this for 3 different binomial random variables so we can see how this behavior works. So the first random variable is x1. Don't get confused that x is a Poisson and x1 is a binomial, x2 is a binomial, and x3 is a binomial. Remember that we want to show that x sub n approaches x, which is a different distribution. So the distribution of x sub n approaches the distribution of x, and these are different distributions in most cases. All right, so we have x is a Poisson 5, or Poisson. I don't speak good French, so pardon that. So we have 3 binomial random variables. So first we have n of 10, p of 1/2. You multiply that, you get 5. 10 times a half is 5. And then 20 and 1/4. Again, n times p there is 5. And 50 times a tenth, or 50 divided by 10 is 5. So we have, n times p is 5 for all of these, and that's what we have to show what we're trying to show here. All right, so we're wanting to find the mgfs of x, x1, x2, and x3. So this is where you need to know your mgfs. So m of x of t is equal to e of lambda e to the t minus 1. Okay, and so we substitute in, that's e to the 5, e to the t minus 1. Now we want the moment generating function for x1, and that's going to be q plus p e to the t. Oops, a little glitch there on my iPad, to the n. And so we can plug in here. So if p is 1/2, q is 1/2. So we have 1/2 plus 1/2 e to the t raised to 10. So n is 10 there. And we can't forget t, so don't forget your range of t, or else you haven't really told the whole story. So we have to know where t is restricted. In this case, it's not restricted, but we should still say that so the person reading it will know. Now, for x sub 2, we have q is going to be 3/4, and then p is 1/4, and e to the t raised to the 20. Okay? And for x3, since p is 1/10, q is 9/10, so plus 1/10, e to the t, and n is 50. And again, put your t, range of t, which is only restricted to the reals here. All right, then we want the graphs of the MGFs to show that as n increases and p decreases, that lambda equals np equals 5. For that, the binomial approaches the Poisson np. So these are some graphs that I made using R. I wasn't really happy with what the book was showing, so I simulated this myself from these different random variables. So what we have is down here on the bottom we have t, okay? And up the top we have m of t. And so the black line is the Poisson, which is what we're talking about approaching. And when we start with this one, which is 10 and 0.5, that's the blue line, you can see that it's the furthest away, okay, overall. The red line is next, so it's a little closer down here, and it's just a little closer up here. It's hard to see up here, but it is just a little bit closer. And then we get to 50 and 0.1, and it gets a lot, well, it's not as close down here, which is interesting for the negative t's, but it is a lot closer in the range from 0 for the positive values. It is a lot closer, okay? So this is just one of the ways that we can see it graphically, but we only have some very limited distributions here. This is what the book had, and their graph was so blurred together you couldn't tell what was happening over in here. So it's not as cut and dried as you might think, okay? So for some values of t, it's gotten closer already. For other values of t, down in here, the green is not the best. The red is still better, and that's the middle one. So you can see that, but then in this region, the green is by far the best, okay? So I hope that demonstrates what's happening here just a little bit. We'll look at some more of these graphs. Obviously, I would not expect you to plot the graphs in this class. All right. Now, let's look at the density of the binomial distribution. It's in blue, and it approaches the density of the Poisson, which is in black. So let's look at these histograms. Again, this is simulations that I performed to show what's happening. So this is 10 and 1/2. And you see that the black, it's not quite symmetrical. However, the binomial is at p equals 0.5. Then we increase, so the Poisson 5 stays the same in every case. So now we have a binomial 20 and 1/4, and you can see that they're getting closer. It's getting closer. And then we have 50 and 0.1, and that's very close. Even though their MGFs weren't as close as we would like sometimes, the actual distributions are. And then the histogram of the binomial 100.1, so I probably should have made this still 5, but I'm not sure if I did 0.05 or if I left it at, is that right, 52, yeah. So I believe this may be 0.05 here, and I just had a typo. Forgot to change it. And look how close these lines are. It's a very good agreement. So that's what's happening here. Okay? So as n increases and p decreases, the approximation gets much better. All right, so let's look at example number 2 here. If I can get it all on the page. So we're going to let y be a binomial 50 over and 1 over 25, or 0.04 for p. And we want to find the probability that y is less than or equal to 1 and estimate this probability using the Poisson distribution. Okay. So we want the probability that y is less than or equal to 1. And remember that this is the probability that y is equal to 0 plus the probability that y is equal to 1. So this is where your Poisson distribution, f of y equals e to the negative lambda, lambda to the y over y factorial, y equals 0, 1, etc. This is where your knowledge of the support is extremely important, or else you might forget this one, right? So you might wonder why I'm emphasizing the support of these functions or distributions, and that is the reason. Okay, so as a binomial, we know that for this is for let's see, no, I'm sorry, this is not y. This is we'll call it x. Sorry, but that was the Poisson. But y, I'm sorry, is a binomial. So now f of y is equal to n choose y, p to the y, q to the n minus y, and y equals 0, 1, etc. You'll notice that it's easier, it's that the support, well, this only goes to n. All right. So the Poisson, at least their support overlaps. Okay? Okay. Now, so I'm going to plug in here, and n is 50, p is 0.04, so 1 divided by 25, make sure I'm right, yes, 0.04. So I have 50, choose 0, and then I have 0.04 to the 0, 0.96 to the 50, plus 50, choose 1, p is 0.04 to the 1, 0.96 to the 49, okay? And when I work this out, so this is going to be 1, this is going to be 1, this is 50, and this is 0.04, of course, okay? And so when I work all this out, I get 0.40048 11967. Okay? And so that's what my calculator gives me. Now, let's do the Poisson approximation. Okay. So I want the probability that y is less than or equal to 1 equals the probability that y equals 0 plus the probability that y equals 1. And here we need to know that, so we can say y is approximately f of y equals e to the negative lambda, lambda to the y over y factorial, y equals 0, 1, and so forth. Okay? So here we need lambda equals np equals 50 times 1 over 25, which is equal to 2. Okay? So lambda is 2. So this is equal to e to the negative 2, 2 to the 0, that's y, over 0 factorial, plus e to the negative 2 times 2 to the 1 over 1 factorial, which is equal to, this is 1, this is 1, so this is e to the negative 2 plus 2e to the negative 2, which is 3e to the negative 2. Now, this is the exact answer, but we want to, and that would be fine, but we want to compare this to the previous example, and this is equal to 0.406058,497. Now, I want to emphasize that right here, some of you are tempted to get your calculator out and calculate this. Do not. If it's this simple, you need to give me this and this the exact, because otherwise you're going to have a rounding error and your answer is going to be different. So please be careful when you can easily, so this value is 2, this value is 1, and they're left in the same terms, and now we can combine them and get a good answer that's exact. I want you to do that, okay? And so now we're going to look at the percent error. Now, the percent error is equal to the approximation minus the actual, well, okay, there we go, divided by the actual as a percentage, okay? So this is equal to, the approximation is 0.4060058,497 minus 0.4004811,967 divided by 0.4004811,967. And now it's okay to approximate. This is 0.013795, which is approximately 1.38% error. That's pretty good, right? Okay. All right. So I hope this gives you a good idea of how this approximation works. Now, in the next video, I'm going to cover the Taylor series expansion. This is a supplemental video. This is not required for the course. It also won't count towards lecture time. So I will post that, and you should definitely review that if you're rusty at all with the Taylor series and the expansion before you go to the next video. Okay, so that's all for this video. If it's applicable, make sure that you update your formula sheet or your list of definitions, your list of distributions. But as always, if you have questions, please come to virtual office hours. I'm happy to help you. If you can't wait, if you need help before then by all means email me and I will get back to you as soon as possible. Until then, please take care of yourself and we'll see you next time.